Alright, so we are continuing our discussion about generating continuous random variables. Last time we stopped with the idea of discussing the methodology that is now that we know as accept reject algorithm, and we also learned how to generate samples from a standard Gaussian using the accept reject algorithm. Now what we're going to be doing in this video is studying a particular specific kind of methodology to generate draws from a standard Gaussian random variable, or standard Gaussian distribution. Now this particular method works a little differently from the ones we've studied, like accept reject algorithm. And the way this method works is in order to generate samples from normal 0, 1, what we're going to do is we are going to draw some random variables which we're going to call r square and theta, and then we're going to generate two random variables, right? The random variables will be called r squared and theta, capital theta, and they're going to be from a specific distribution. Exactly what distribution we don't know yet. We'll learn what distribution, but these are essentially going to be generated using a distribution in what we call the polar coordinate system. And then we will basically take these two samples, r square and theta, and transform them using some transformation h into h of r square and theta that we hope that once we apply that transformation, we hope that this will be true. Okay? And this is a trick that we'll actually use fairly often, which is that we hope to generate using draws from one distribution. We do some transformation from the draws of that distribution to go to some other random variable that is now a draw from some other distribution. Okay. Now, in order to understand exactly what type of distribution is r square and theta going to be from, we're going to need some theory. Okay, and to understand the theory, we set the following setup. Is, let's say we consider capital X and capital Y be two independent and identically distributed Gaussian random variables. Okay, so X and Y are IID, independent, identically distributed as normal 0, 1. Then if they're independent and normal 0, 1 distributed, I can easily write down the joint density of X and Y. Right? So now the joint density of X and Y is basically f of xy, which denotes the joint density, but then this is nothing but f of x times f of y, where f of x is the PDF of normal 0, 1. Right? And we can do this, write f of x comma y as f of x times f of y, because my random variables x and y are independent. Right? But I know that the PDF of a normal 0, 1 is nothing but square root 1 over 2 pi e to the power minus x squared by 2. Right? And I take that form and I put that exactly here. Right? And I put that for f of x and f of y, and this gives me the joint PDF of x and y, right? The tuple, the together x comma y. All right. Now what I'm going to do is I'm going to map x and y to which is present in the Euclidean coordinates. I'm going to map it to its corresponding polar coordinates. So the idea over here is that if I have axes, right, this is my x-axis and this is my y-axis, okay, and if I have a point over here, okay, this point has its x coordinate, so its x value as this thing and y value as this thing, okay, and it's this point over here. Now this point is on the Euclidean coordinate system in the sense that it is on the standard axis of x and y. Now the question is, in what ways can I describe this point? Right? Can I find the location of this point some other way? So one way is to find its location on the x-axis and find its location on the y-axis, and wherever those two lines meet is going to be my point. That's one way. Another way to find the exact location of this point on this plane is to find the origin, which is going to be this point here, and then find how far is this point from the origin and at what angle is this point from the origin. Okay, so if from the origin and from this line over here, if I can find the angle and the length of the point from the origin, then that together will give me the distance of the point from the origin. Then that and the angle together will help me identify this point. Okay, so again I repeat that any point on the x and y plane can be either identified by x and y, or it can be exactly identified by a line connecting the origin to that point, right, and the length of the line and the angle of that line. All right, so that's exactly what we are going to try and study here. So now what we'll do is we will take this line, okay, and measure the angle over here. So now the line that we draw, the distance from this dot to this dot, this distance measured by this orange line is something we denote by r squared, and because it's a distance, it's always going to be positive, right? So I'm measuring how far away something is from the origin, so it's always going to be, let me say, non-negative. It can be 0 if the point is origin itself. Further, I also have the angle theta over here, right? Let me actually write it in capitals, because I'm doing everything in capitals. I have theta here as well. Okay, so the same point x and y can be mapped as r squared comma theta. That's the idea. Okay? So the point x comma y can be mapped to r squared comma theta. It's the same point. And we use exactly that. So what's the relationship of x, y with r square and theta, right? That's what I want to understand. So how are x and y and r square and theta related to each other? Right? And you can see that this is not too difficult to figure out, because if I look at this part over here, then I know that x squared plus y squared has to equal to the hypotenuse, right? So that's one relationship that I have, right? And then the other relationship I have is that the angle over here must be a function of the tan of the x and y plane objects, right? So that's how we convert to the polar coordinate system, right? What I mean by that is, very specifically, if I denote r squared and theta to be the polar coordinate version of x and y, then I have x, this distance, being equal to nothing but r cosine theta, and this distance, which is this over here, y, nothing but r sine theta. Okay, and if I do that, I also note here that what is the support of r. Now, because x and y are random variables, r and theta are also random variables. So what is the support of r? The support of r is all positive, because distance has to be non-negative, right? So it's 0 to infinity. Technically, you can include 0 if you'd like to. And the support of theta, the angle, is either from 0 to 2 pi, right? So it can be anywhere from 0 to 2 pi. All possible angles are probable given any point anywhere on the plane, right? Then particularly I can move this relationship around to also get r squared is equal to x squared plus y squared. This we know, because we know that the hypotenuse is equal to the square of the other two sides, and tan of theta, so tan of this angle, is nothing but y divided by x, right? Okay, right? So in this way, I can take any xy point and map it to r squared and theta. Alright, now why is this helpful? Well, what I realize is once I do this, okay, and remember x and y are distributed according to standard normal, independent of each other. Okay? Now what I do is I have r square and theta being the random variables, and the realizations of these random variables I will denote by small d and theta respectively, right? So r squared will take values d and capital theta will take values theta. And what I want to do is find the joint density of f, d and theta. So there is a sub notation embedded here. Whoa, sorry. There is a sub notation embedded here that this is r squared comma theta. Okay, that's a sub notation embedded in this density formulation. Okay, so I want to find the joint density of that. Okay? So using this relationship over here and this relationship, I know that small d is equal to small x squared plus y squared, and small theta is equal to tan inverse of y by x. Now, if I want to take x and y, right, and I'm mapping x and y to r squared and theta, okay, and I have the density of f of x, y, and I want to know what happens to the density of f and d comma theta. Okay, this is what I want to know. And through the transformation of variables mapping that we've learned, we know that this is critically dependent on the Jacobian of the transformation. So first I need to find the Jacobian of the transformation, right? So to find the Jacobian, f of d comma theta is nothing but the Jacobian times f of x comma theta, right? Alright. So basically now my goal is to find the Jacobian here. Okay. Now the Jacobian here is del x by del d in the first element. So it's the determinant of this matrix, del x by del d, del y by del d, del x by del theta and del y by del theta. Now x over here, remember, is going to be x is square root of d cosine theta and y is square root of d sine theta. So I have j, my Jacobian is equal to the determinant of del square root d cos theta by del d and del square root d sine theta by del d. Similarly by del theta by del theta. Now, when I take partial derivative with respect to d here, cos theta is a constant term, so it comes outside. I get 1 by 2 because of the square root over here, right? And then I get a square root d term in the denominator. Similarly, sine theta is a constant here, and I get 1 by 2 square root d. Okay. Now when I take partial derivative with respect to theta, the partial square root d is just a constant, and the partial derivative of cos theta with respect to theta is minus sine theta, and then this is square root cos theta. Now in order to find the Jacobian, as in the determinant, I multiply this and add this, but I notice there's a step missing here, so let me write that down. When I multiply this, I basically get this is equal to 1 by 2 cos square theta plus 1 by 2 sine square theta. And because cos square theta plus sine square theta is equal to 1, I immediately get this is equal to a half. Alright. So that gives me that the Jacobian is just a half, which means I can go back to this equation which would tell me the actual distribution of the joint density of r squared and theta to be the Jacobian times the density of x and y. Now, I know that d is equal to x squared plus y squared, so the joint density of r squared theta is f d comma theta with. Now remember, f of x comma y is nothing but 1 over 2 pi e to the power minus x square by 2 e to the power minus y square by 2, which is equal to 1 over 2 pi e to the power minus 1 by 2 x square plus y square. Okay, and what we're going to do is we're going to use this here because I know that f of x is equal to this expression over here. So I get 1 by 2 coming from the Jacobian. Then I get 1 by 2 coming from this, 2 pi coming from this. Then I have e to the power minus half times x squared plus y squared, which is a function of d, and theta is just d by 2. Right? That's it. And d is defined from 0 to infinity because that's my support for r squared, and theta is defined from 0 to 2 pi because that's my support for theta. Okay? But what does this density look like? What I'm trying to do, remember, is I'm trying to map to some r squared and theta so that I can actually sample from that r squared and theta and then transform back to get my normal random variables. In order to do that, we started from normal random variables, did a bunch of transformations over here, right? And then we get something as to be the density of the r squared and theta, right? But what I notice is this e to the power minus d by 2 along with this half is, with the fact that d is defined from 0 to infinity, is actually the PDF of exponential 2, right? An exponential distribution with the rate parameter 2. And the 1 by 2, with the fact that theta is defined between 0 and 2 pi, this thing is nothing but the uniform distribution on 0 and 2 pi. Further, I see that this and this are completely separable, which means that these are actually independent of each other. And that gives me a great way to actually simulate this random variable, because I get that because this is a separable density, right? So r square and theta are independent of each other, and further theta is distributed from 0 to 2 pi and r squared is exponential 2. So what I do now, using this fact, what I can do is I can generate r squared from exponential 2, generate theta from uniform 0 to 2 pi, and then transform r squared comma theta to x and y using the transformations that we've just discussed. If we do that, then x and y will be IID normal 0, 1. Right? So we started with, in getting to this point, we started with x and y being normal 0, 1, and then we basically did the steps to get to the fact that these are exponential and uniformly distributed. Now we use this fact practically in the way that we can generate r squared from exponential 2 and theta from uniform 0 to 2 pi, and then map back to get my IID normals. Okay. To generate from exponential 2, we know we can do this using the inverse transform method. We've done this before. Okay. And if u is uniform 0, 1, then by the inverse transform method, just by the logic we've done for exponential 1, we get that minus 2 log u is exponential 2. This is just using inverse transform. And to generate u from uniform from 0 to 2 pi, we know we can obtain a different u from 0 to 2 from uniform 0 to 1, and then find 2 pi u is going to be distributed from uniformly from 0 to 2 pi. Which means that we finally get the following algorithm. We generate two, this is the Box-Muller algorithm. We generate two uniforms u1 and u2 independently from uniform 0, 1. Okay, two uniforms independent. We set r squared to be equal to minus 2 log u1 and theta to be equal to 2 pi u2. Okay, that means this thing is now exponentially distributed. Okay. So this part is now exponentially distributed. This is exponentially distributed with rate parameter 2, and this part is uniformly distributed between 0 and 2 pi. Then we do the transformation that got us these r squared and thetas. We set x to be equal to r cosine theta, which is nothing but square root minus 2 log u1 cosine 2 pi u2, and y is r sine theta, which is square root minus 2 log u1 and sine 2 pi u2. Okay, That gives us the Box-Muller transformation. Now what you have to note is that you actually get two draws from normal 0, 1, right? So we we actually get two draws from normal 0, 1 using this method. Right? We don't get one, which is typically what would happen in the accept reject algorithm or the inverse transform algorithm. We get two draws. And this makes sense because we actually start from two draws from the uniform as well. So if we could do inverse transform, we would have done one uniform draw to give us one normal draw. Now here we do two uniform draws to give us two normal draws. So this is the Box-Muller algorithm.